Alright, so we're very happy to have Henry Lin from Stanford who will tell us about a symmetry algebra and double-scale SYK.
Thanks very much, and yeah, super happy to be here. This work is mostly based on this paper that appeared a while back with Douglas, and yeah, it's also many other works with this HEP-QIS public recording. All right, so let's start with something fun. Okay, so JT gravity, you were great. I don't think anybody disagrees with that statement. You are exactly solvable, so these are the reasons why JT gravity is great, right? So it was solved by many people in many different ways. All correlation functions are known exactly. And we also know you're an holographic dual, right? Yeah, so you're very great. But maybe it's time we move on. Okay. I would say that it's me, not okay. Why do I say this? Because, well, for one thing, we don't have the propagating matter in JT. JT is also always maximally chaotic. And third, it's already UV complete. So there are no signs of strings, branes, etc. Now, these might sound like good things, but, and I agree that there's certainly good things for understanding the simplest model. But if we want to understand, let's say, black holes more generally and quantum gravity, I think we typically will want to have all three of these things not be true. So I'm certainly not trying to rag on JT gravity, but I'm saying that if we want to eventually understand, quantum black holes, we would probably have to confront these kind of issues. Okay, so that turns me to my sort of new interest, which is double-scale.
What was the?
Yeah.
What was wrong with me being UV complete?
Nothing. But it's in some sense a very simple UV completion. So I would just like to explore more complicated UV completions. Well, it's related to these other statements, right? So if it has a simple UV completion, it will always be maximum.
But it's not that you don't want UV complete. You want something that's not. It's simply.
Yeah, that's right. I would like a more, well, maybe I want it, maybe I don't, but for now I want a richer UV completion, let's say.
I feel like the problem of the first two, and yeah, it's like the third one is
like
if JT gravity described our universe and was UV complete, then we'd
that's
really done. We'd move on.
I guess it's only a problem if you want to understand, like, let's say string theory or something, right? If you want to understand other theories that are UV completed,
or like
ways that are more
universe.
Yeah. Some of us want to understand our universe. I also think that it's sort of related to these two. I mean, all three issues are really kind of related, right? The fact that there's no propagating matter is also related to, so these are really all just one issue in some sense. All right, so some people have now turned their interest to double-scale SYK. By some people, I mean me. And it retains the nice feature that it's still exactly solvable, but it sort of overcomes the previous three issues, at least in some ways. I'm certainly not convinced that double-scale SYK is as rich of a theory as, let's say, n equals 4 3, but it's a little bit richer than JT gravity. So in particular, there's some new physical effects in double-scale SYK that are not present in JT gravity. And I think that it's the simplest model, for example, where we can try to address some of these questions. So for those questions, for example, today I will focus on submaximal chaos, where there's some regime in which double-scale SYK is maximally chaotic, but then there's some bigger regime where it's not. And so a simple question is how to understand the bulk physics when it's not maximally chaotic. Okay, so that's the sort of angle that I'm going to take today. Okay, so just a reminder, right, according to...
Just to ask about the second one.
Yeah.
What sense would you say double-scaled SYK is a better way of adding matter than just put matter in JT?
No way in particular. No. Except to say that presumably there's something like the trumpet in double-scaled SYK, and it doesn't have UV divergence. Okay. But we don't really know what it is yet, so... All right, so according to Einstein gravity, black holes are maximally chaotic systems, right? They have this chaos exponent. And one point of view on this chaos exponent is that it is a consequence of the near horizon symmetries of the black hole. So, for example, if we consider nearly near extremal black holes, the near horizon symmetry is SL2. That is the symmetry group of the nearly ADS2 throat of a near extremal black hole. Okay? And so I've drawn the three symmetries of SL2 here, right? This is the global energy, this is like momentum, and this is like boost. All right, these generators move matter with respect to the Schwarzschild, preserving the length of the warp length. So they do so in a way that is actually completely gauge fixed and totally like kosher. There exist some gauge invariant operators that actually do the three things that I said. And these three generators can also be depicted in Euclidean signature, which I've done here. And they satisfy an SL2 algebra. So in particular, the boost commutator with P plus and P minus satisfies this very simple algebra. Right? Okay, so how is this related to chaos? Well, we can simply conjugate one of these momentum generators, let's say P minus, with the boost Hamiltonian, right? And we see that it will grow exponentially with a chaos exponent 2 pi over beta. Okay, so this is the simplest way in which we can derive the chaos exponent from the geometry of the black hole. First by noting its symmetries, and then using its symmetry algebra to compute the exponent. Now, to understand why P minus is relevant, why it's important to consider that particular operator, we can consider 2-to-2 gravitational scattering. Right? So in 2-to-2 gravitational scattering, we have some particle, let's say this W particle, which acts as a shock wave for another particle in red. Right? So this other particle in red, it crosses the shock wave, it experiences a Shapiro time delay, and it ends up here. Right? Near the horizon of the black hole, right, this thing here is nothing but P minus. It's the null generator momentum near the horizon. So that's why P minus is relevant. That completes the derivation of the chaos exponent, let's say, for near extremal black holes. Okay, so that was the case in general relativity. Now let's go to string theory. So Douglas and Steve analyzed this in this paper. And they taught us that in general, the chaos exponent is modified. So instead of being 2 pi over beta, it's 2 pi v over beta, where v is less than 1. And the reason why it's less than 1 is closely related to the stringy physics, right? So strings are, I won't redo this in detail, but the only thing you need to know is that strings are somewhat messier processes. They allow for messier processes. And so the inelastic effects of string theory are somewhat related to the fact that the chaos exponent can be smaller than 1. Now, ideally, we would like a computation of this chaos exponent in some theory, like n+4 super Young mills, at finite temperature and at finite temperature parameter. Okay? So that would allow us to compute this exponent in string theory, let's say AS5 and S5. Okay. But we do not know how to compute correlators in n=4 at finite temperature. Okay, in this limit. So we do not know how to compute this exponent. But the reason why we talk about double-scaled SYK or large P SYK is that we actually know how to compute this exponent. And it was done already in Malazan and Stanford. Okay. So they computed this chaos exponent, they found it's less than 1. It's given by this very simple formula. Okay? So you should think of V as the solution to this equation. So you put in beta J and it tells you what V is. So at very low temperatures, V is very close to 1, and the chaos exponent is close to maximum. Right? But at finite temperatures, it's a finite fraction of the maximal chaos exponent. Okay, so at very high temperatures, the fraction can be quite small. So there's a very big deviation between the maximal chaos exponent and the actual chaos exponent of this theory. So the simple question is just, how do we explain this chaos exponent, which was computed, let's say, using boundary methods, from a bulk perspective? And the strategy will be to take a scenic detour. So scenic detour means that we will consider a more complicated limit, which is the double-scale limit. It's a more general theory than just the large PSYK. So that sounds like a harder thing to do, right? And instead of just studying a special theory, we go to a slightly more general limit. But the advantage is that in that double-scale limit, there is some sort of bulk Hilbert space. And using that bulk Hilbert space, we will be able to find the symmetries that are analogous to this SL2 symmetry that I explained in the general relativity case. And from analyzing the symmetries, we will get some sort of bulk picture, which will emerge when we come back to the large P limit. So that will be hopefully clear later on. But when we do this procedure, by going to this double scale theory and coming back, we will gain something, which is some sort of exotic notion of geometry. It won't be standard geometry in the sense of Einstein and so forth. It will be some sort of unusual bulk geometry. And this is what we call fake geometry. At the moment, it's somewhat of a name, and we certainly don't understand many aspects of the fake geometry as well as we would like to, at least. Okay. Now, here's the SYK model. It has three-dimensional parameters, n, the total number of fermions, p, the number of fermions participating in the interaction, and beta j. Okay? So those are three-dimensional parameters. We will be considering in this talk the limits where n goes to infinity and p goes to infinity. So this is sometimes referred to, well, before I say more, you do not know whether I'm talking about large p SYK or double scale SYK. So the nomenclature is that the double scale limit is when you hold the ratio n over p squared fixed and beta j fixed. So those are the two remaining dimensionless parameters of the theory. Okay? And the large p limit refers to taking first n goes to infinity and then p goes to infinity, right? So that would be like n over p squared, very, very big. Okay. Just to make sure that's completely clear, because this often confuses people. Double scale limit, you can hold n over p squared fixed, beta j fixed, but n to infinity, right? If you want to get large p SYK, you go in this direction in parameter space, okay? And if you want to get something like JT gravity, you go in the diagonal direction. Okay, that's sometimes called the triple scaling limit. So it's one theory with many different limits, and the ones that we're most interested in is, let's say, the large p SYK limit. But as I mentioned earlier, we're going to approach it by first studying this theory and then coming back. Okay. The case where we understand is JT gravity, right? So, yeah, roughly the strategy was we start from JT gravity, we get maximal chaos, we go and analyze the double scale theory, and then we come return to this. Yes.
And for JT gravity, you're saying that you're also need to take the large p limit?
Yes. Well, okay. Sorry. I've already taken p to infinity in this talk, so.
Okay.
Yeah.
Okay.
Yeah. So it's true that you can get JT gravity also with p fixed and going to low temperature, but for this talk, I'm always going to be interested in the large p model. Yeah. So I apologize for all the notation. Please, if you're not familiar with this kind of notation, it's a little bit dizzying, so interrupt if you forget what the different words mean. Okay, and it's also convenient to introduce this parameter lambda, which is 2p squared over n. That's fixed in the double scale limit. When lambda is 0, that is the large p SYK model. When lambda is held fixed, okay, it's a double scale limit. Now, the reason why we do this is because, first of all, the double scale theory is technically useful. So it has this chord method, which I'll explain in a second. And this chord method actually has an interesting history. So, for example, the computation of the Schwarzian density of states, the famous sinh square root of E, was actually first done using something which we can now call chords. It actually predates the computation that was done by Stanford and Witten. So they actually first did it in double scale SYK. They noticed that it was one loop exact, and they said, huh, and then they tried to explain it in a pure JT context. Okay. So in some sense, it's actually easier to do computations using the chords than it is using other methods. That's not always true, of course. It's just for some points of view it is. Also, the computation of endpoint functions in this theory are completely known. And as a little advertisement, for example, if you're interested in super SYK, you can get the number of ground states in the n equals to 2 model exactly, well, in the double scale limit using these chord methods. And that includes some non-perturbative corrections in n over p squared. So the chord theory knows about certain non-perturbative corrections. So this is just to tell you that the chord theory is technically a nice tool, but it's also conceptually interesting. And it's conceptually interesting because it allows us to define some sort of bulk Hilbert space. Okay. Another reason is that it's conceptually interesting is that it seems to give some sort of discrete UV completion of gravity. And this discrete UV completion of gravity is somehow compatible with JT gravity and ordinary, let's say, Einstein gravity emerging in some limit. So of course this is something that some people wanted in higher dimensions. It's probably not possible in higher dimensions, but it is possible in low dimensional gravity. So if you like, you can think of the chords as a bit analogous to planar diagrams. If you're familiar with how the minimal string emerges from planar diagrams, the way that JT gravity or Hopf geometry emerges is similar in many respects to how the continuous world shape appears from these discrete structures.
So did you, so there are these arguments by Polchinski or
Right.
about in higher dimensions when you break UV, like Lorentz invariance, it like flows to the...
Yeah, those arguments don't seem to go through it
into the...
Yeah. And in particular, I think this is a concrete model where there's a control breaking of the Lorentz invariance. So the control breaking of Lorentz invariance is somehow controlled by this Q deformation, which we'll see.
Would that be a concern that you're introducing ingredients which are sort of from the start, cannot generalize?
Yes, that is a possible concern. I don't have I don't have a clear answer to that. I think, I could say some vague things about, Q deformations and so forth. Maybe they show up in this amplitude, right? I can offer some speculations, but I agree that that is a possible worry. That perhaps we're just studying some model that has nothing to do with string theory and so forth.
Is there some other way of thinking about how to do the higher dimensions where what looks like an explicit breaking of Lorentz invariance here is
Somehow this is
softer?
Well, yeah, I mean, I think the way that we break Lorentz invariance is very subtle, even in the two-dimensional case, as you'll see. So it's not something, it's not even as, it's more subtle than just discretizing the string world sheet with planar diagrams, for example. Maybe we should discuss that more at the end. I think in 3 dimensions there's probably something similar. Whether there's anything like that in higher, even higher than 3 dimensions is an open question. So I don't really know the answer. Okay, so now I told you why chords rule. Now I'm explaining chord rules. Okay, so sorry for that. So the chord rules are extremely simple. I have explained them several times, but I will explain it once more. The chord rules just involve drawing Wick contractions between like operators. So the idea is you want to compute some object, let's say like trace H cubed, some insertion of matter operators, and some powers of the Hamiltonian in between them, right? So you just draw a circle, and you arrange, you draw points for each operator. So you have a black point for each Hamiltonian insertion, and a green point for each matter operator insertion. Okay. And then you draw all possible Wick contractions that connect these points, right? And then the rule is that every time there's an intersection between chords, you write down a factor of Q, which is e to the minus lambda. Okay? That's for intersections of black chords, right? For intersections of a green chord with a black chord, you write down a factor of R, which is e to the minus lambda times delta. So delta is defined by P prime over P, where P prime is the length of the operator that appears in the matter chord. Okay, so you can think of this as very similar to a Hamiltonian chord, right? Except that it's a bigger operator. Potentially, it could be composed of P prime fermions as opposed to the Hamiltonian, which is composed of exactly P fermions. So there's some very simple Feynman rules, and in this case, right, there's 2 intersections between this green and black, between green and black chords. So you have a factor of, there's 3 intersections, so you get a factor of R cubed, and then 2 black intersections, which gives you a factor of Q squared.
Is there any intuition on why these are the rules, or you just need to look?
Yeah. So the intuition is that, well, you can ask, why does lambda appear, right? And the intuition is you have, so let's try to write down what that is. So the Hamiltonian will be like psi I1 up to psi p. There will be some random complex, right? For each Hamiltonian, there will be a different factor. There will be one factor of j, right? The j's are distributed in some Gaussian distribution, so you need to do Wick contractions. So that explains the Wick contractions. Now, why are there these intersection factors? Well, that's because you will need to compute fermions past each other. So in order to evaluate this trace, it's just a trace of a bunch of fermions, right? But you see, you'll need, in order to simplify it, you'll need to use the rule trace of I squared. You want to use the Majorana algebra, right? So in order to apply that, you need to compute this guy all the way through a bunch of these guys. And when you do that, you can pick up a minus sign. So whether you pick up a minus sign or a plus sign depends on the number of guys that you pass through. Okay. And at the end of the day, the thing that is relevant is the probability that in this set of fermions and in this set of fermions, you have some like fermion. So these are a bunch of indices, right? You're summing over them. And you can ask, what is the probability that the sum fermion appears in this sum, in this term? And it also appears here, right? And so that is controlled by p squared over n, right? So you get a factor of p over n for each factor, right? And then you multiply by n because there's, n possible choices of fermions. So p over n times p over n times n is this factor p squared over n. So this explains this factor of lambda, and more accurately, you can compute the probability of double intersection and so forth, and those will be distributed by some Poisson thing, by some Poisson distribution, and that's how you get this e to the minus lambda. Okay, thank you. So it just comes from something extremely dumb, which is just literally expanding down powers of the Hamiltonian and doing the Wick contraction rules. Okay, that's all it comes from. Okay, so, right. So just to summarize, if we want to compute some correlator, we write down all possible Wick contractions, we put some penalty factors for each intersection, and then we sum over all possible Wick contractions. Okay. Now, that was actually used to compute these correlation functions. People understand how to actually do the combinatorics of these Wick diagrams very well, and so they can compute correlation functions. But another thing that's interesting is that you can define a two-sided bulk Hilbert space by slicing open these diagrams. Okay? So here I've depicted some typical chord diagram, and I slice it open, and according to this gray slice, I will encounter a black chord, a green chord, and a black chord, right? So I can denote a particular state that appears on that slice in this schematic way. Okay? I also have a notation where I label it by NL, NR, where NL is the number of black chords that appear to the left of this green particle, and NR is the number of black chords which appear to the right of the green particle. Okay? So that gives me some way of labeling states with exactly one green chord, but any arbitrary number of black chords. And on this Hilbert space, we can work out easily what the Hamiltonian does when it acts on this Hilbert space. So let's consider the action of the right Hamiltonian. All right, so it can do two things. Let's say it acts on a state with 6 chords. One thing that it can do is it can create a chord. Okay? Another thing that it can do is it can annihilate a chord. And we choose a convention where all intersections happen whenever the chord gets annihilated. So in this particular case, we could annihilate this chord, and if we do so, it has to pass these chords, and it gets a factor of q cubed. Right? And at the end of the day, we need to sum over which chord it annihilated. It could have annihilated the 4th chord, or the 5th chord, or the 6th chord, right? And that gives us. Yeah, so when you sum over the different ways of which chord could be annihilated, you do this sum, right? And this sum gives you the so-called q-deformed integer, 1 minus q to the n over 1 minus q. Okay. So you see, the expression for the Hamiltonian is something very simple. It's just a creation operator and an annihilation operator. But the annihilation operator comes with this funny factor. Okay. Now that was the case with no green particle. Let's now go to the case with the green chord. Okay. So now we have some number of green black chords to the left and some number of black chords to the right. We act again with the Hamiltonian. Okay. Now there are 3 possible things that can happen. We can create a chord on the right. So that's this term. That's this term. Or we can annihilate a chord. If we annihilate a chord, we can either annihilate a right chord or we can annihilate a left chord. Right? We can annihilate some chords on the right to the green particle, or to the left of the gray part. And they get their own combinatorial factors, right? So this is this Q-deformed mixture that appeared before. So the point is just that there's an extremely simple form of the Hamiltonians in terms of these creation and annihilation operators. And similarly for the left Hamiltonian. So now I can tell you what the chord algebra is. So the chord algebra that we discussed is generated by three operators: h left, h right, and one more operator, which is the total chord number. Yes?
Sorry, I think I missed something in the previous slides. Are these Hamiltonians still the SYK Hamiltonian? And if so,
That's
how are
correct.
you writing them as just the creation of Hamiltonian?
That's correct. Okay, so, good, thanks. So, these Hamiltonians are expressions for how the SYK Hamiltonian acts on the Hilbert space that I defined. So, they're a special class of states that survive the double scale limit. So these are states where we only have inserted, let's say, a finite number of boundary Hamiltonians in the thermal field double, and potentially some number of green matter operators. Okay, so if you like, that's the sort of code subspace that I'm considering. But I'm considering an arbitrary number of Hamiltonian insertions and an arbitrary number of operator insertions, as long as it's finite. So that's actually quite a very large, I mean, it's an infinite dimensional subspace of states. Yeah, so, yeah, we could be a little bit more precise about that. Type 2, 1, blah, blah, blah. All right, you can ask Jeff about this. All right. Okay, so I told you what h left and h right are. They're just the left and right SYK Hamiltonians acting on the subspace. And then there's one more operator, which is the total chord number. So let me go explain what the total chord number is now. So it's what it sounds like. It just counts the total number of chords weighted by delta. So a black Hamiltonian chord gets a weight of 1. If you have a matter chord, it gets a weight delta, where delta was p prime over p. Okay. And I will argue that this is some sort of discrete analog of the length of the Einstein-Rosen bridge. Right? So we should think of the bulk dual of SYK as some sort of wormhole geometry. And this n bar is literally the length of the Einstein-Rosen bridge in that discrete geometry. Okay. So microscopically, we can say a little bit more about what n bar is. So I told you that h left and h right are microscopically just the SYK Hamiltonian. Microscopically, we can also say that n bar is just given by the so-called size operator. So the size operator has this expression, but I can just define it a little bit better. So if I start with the maximally entangled state, this is a two-sided state, maximally entangled state. If I act with psi1, the size operator acting on this thing just returns psi1 omega. If I act on a state, let's say psi1, psi2, it returns the same state with a factor of 2, and so on. If psi1 appears multiple times, I use the Majorana fermion algebra first to simplify it, and then I will just get psi2, right? So it counts the total number of fermions once I've done all possible simplifications using the Majorana algebra. Okay, that's why we call it the size.
Is the definition of it being weighted by delta, is that just to have it be the size operator microscopically?
Yes.
Like,
but it's actually very natural. So if we chose not to weight it by delta, we actually would not find a closed algebra. So the factors of delta would then appear in the algebra. So if you put if you define it like this, it's very natural.
because in the sort of actual JT limit, I think the number of Hamiltonian chords will become infinite, and probably the number of backward ones is finite, and maybe you don't.
That's right. You don't really care.
Matter
I
very
think
much.
the one case you would care is if you scale the size of the operator to be very large while taking the triple scaling limit. So, like if you keep G Newton times the mass fixed, basically, then you would care.
Yeah.
All right. So, what is the algebra formed by those three operators? Well, it's actually quite simple. So, first of all, let's split all the Hamiltonians into creation and annihilation. Right. So, as I said before, there's always terms which create chords, and there's terms which annihilate chords. We do that both for the left and right. This part of the algebra, right? This looks like harmonic oscillator algebra, right? You have two harmonic oscillators, A left and A right, and these are the relations you would expect to see for harmonic oscillation, creation, and annihilation operators. The only thing is this little q, right? So this q means instead of the ordinary commutator, you have the q-deformed commutator. And that was related to these funny q numbers that we saw appearing in the combinatorics before. Okay, but then there's like one sort of non-trivial thing about the algebra. Yeah. So there's one sort of non-trivial relation which says that the left annihilation operator does not commute with the right creation operator. So this is the sort of non-trivial relation because it says that the pair of Q-deformed harmonic oscillators are not decoupled. So this makes the algebra much richer. Okay, now it doesn't look obvious from the way I presented it, but you can actually check that in the triple scaling limit, where we get JT gravity, this thing gives you the so-called JT gravitational algebra that Harlow and Wu wrote down. Okay. So it's some exercise in doing, well, whatever, okay, it's some exercise. I won't go too much into it, but for example, part of this algebra is very intuitive, right? The left Hamiltonian commutes with the right Hamiltonian. The left momentum commutes with the right momentum. The length commutes with the momentum gives you I, right? So that's the Heisenberg part. And secretly, you can actually rewrite this whole thing as basically just SL2 times Heisenberg. Okay? But this whole algebra is actually secretly just generated by an SL2 algebra times a Heisenberg algebra, even though it looks complicated in this presentation. Okay, so that was that was the evidence that we correctly identified the core number as a length. Okay, so if you define the length to be lambda times the core number, okay, then you will see in the triple scaling limit that this operator, according to the previous algebra, satisfies all the algebraic relations that you expect the length to satisfy in JT gravity. So that shows that this core number is really the length in the JT gravity limit. And then we just define it to also be some sort of length away from that limit. Okay. Now, this algebra actually has a little bit more structure, which will be important for understanding it. And it is actually something called a bialgebra. Okay. So what is a bialgebra? Well, let's remember what an algebra is. An algebra is a vector space equipped with some multiplication rule, an associative product. So that takes two copies of the algebra, and you multiply things so you get one copy of the algebra, right? Now, a bialgebra is basically the opposite thing. So it has something called the coproduct. The coproduct takes one copy of the algebra and gives you something in the tensor product of the algebra. Okay. And this coproduct is compatible with the multiplication in the algebra. So that technically means that we say that the coproduct defines some sort of algebra homomorphism. Okay. So here is the explicit definition of the coproduct for this particular algebra. So it just maps A dagger left, for example, to A dagger left tensor identity. And it maps, for example, the total core number into the sum of the core numbers of the left and the right tensor factors. But the non-trivial thing is that it maps the annihilation operator into something somewhat complicated. And you can show that for any choice of delta, so delta is just a parameter now in the coproduct. For any choice of delta, this definition, along with the analogous definitions for the right creation and annihilation operators, they satisfy the algebra homomorphism property. Okay, so you can, as an exercise, check that some of these commutators that I wrote down in the previous slides are satisfied when you use this definition of the coproduct. All right, so what does this stuff mean? Okay, so the idea is that it's actually something very physical. It basically, the coproduct tells you how to join wormholes together. So this is something a little bit weird, but let me do my best to explain. So we have two states in the two-sided Hilbert spaces, right? So this state is a state in the two-sided Hilbert space. We should think of it as some Einstein-Rosen bridge with some matter particle, let's say a red matter particle sitting in the middle of the bridge. Right? Here we have another Einstein-Rosen bridge, and what we literally do is we concatenate the head of the wormhole to the tail of the other wormhole. And when we do that, we have the option of putting a matter particle in between those two things. So that's this blue thing. Okay, so that defines some mapping of two copies of the tensor, the tensor product of Hilbert spaces into one copy of the Hilbert space. And the claim is we can also define a delta inverse, and the claim is that the coproduct is the natural action of the algebra when we consider these joining and splitting operators. So more explicitly, if we want to know how the coproduct acts, we basically consider the two states as a single state by joining them together and adding a blue matter particle. And then we split them apart again, and that defines how the coproduct now acts on two copies of the algebra.
So for every matter field choice, you have one delta.
That's correct. That's correct. So the coproduct comes with a one parameter family of coproducts, really, which are labeled by what this blue particle actually is. And in particular, it's labeled by, let's say, the mass. In a theory, let's say with global symmetries or something, it'd also be labeled by the charges carried by this matter particle. Okay, so it tells you when you, I mean, if you're normally in like a quantum field theory, we never discuss this kind of splitting of states, right? Because that would make a very high energy thing. And so this blue particle you can think of as that very high energy thing. So we split the state, right? So we take the state, we sort of split it, and we delete that high energy thing that we.
How's delta inverse defined if there's more than one blue particle? Or do you
yeah, it's not. It's not. So it's defined only on the space where there's exactly one.
And it's delta is defined on spaces that don't have any blue particles.
That's right. That's right. That's right.
Henry, when you say that it's related to the factorization problem, you don't mean that this shows that the original Hilbert space was matter factorized.
No, I don't mean that, yeah. But I mean that it sort of does the next best thing. So ideally, you'd like the two-sided Hilbert space to factorize into a product of one-sided Hilbert spaces. But here, the two-sided Hilbert space factorizes into products of two-sided Hilbert spaces. So this is like something that can happen in like type 2-1 that can't happen. It's basically as close as you can get to resolving this without actually resolving it. That's what I mean. I can give you a slightly more formal.
But we actually expect that it does factorize.
Yes, yes.
Even if we kept Q finite.
Well, yes, if we kept n finite and so forth, it would actually factorize. But here we define some subspace of states, and the statement is that it's a very large subspace of states. If we defined it to be all possible states, then it would just be the type 1 discussion, and it would factorize.
I guess my point is that that wouldn't be explained by chords.
Yeah, you would need to go, well.
You'd need to go beyond
You need to either go beyond, well, maybe there's still some chord discussion, but it would involve these wormholes and all sorts of crazy things, right? It'd be like wormholes with chords and all that stuff.
Okay.
Yeah, it would go beyond the approximation that I discussed here, for sure. Okay, so, okay, let's just finish this abstract exercise and then we'll get to the fun part. Okay. So now let's try to classify all particular irreducible representations of this algebra. Okay, so first of all, there's one very obvious irrep of this algebra, which is just all states of the empty wormhole. So that means states with no matter particles, and they are labeled just by the integer n, where n is the total number of chords, right? That is an irreducible representation of the chord algebra, where h left is equal to h right. So we call it a short representation. Then there are one particle irreps. Those are states with exactly one matter particle. Okay, so those are labeled by NL, NR, and they are somehow highest weight irreps of this chord algebra, meaning that AL acting on this primary state annihilates it, and then we can build up all other states like NL, NR by acting with the creation operators. And the claim is that these are the only irreps that ever show up in double-scale SYK in this limit. So all other states, including the ones with multi-particles and so forth, they can be reduced down to these two categories of irreps. So the problem that remains is to reduce a general state in double-scale SYK, which can have lots of different matter particles, red particles, green particles, blue particles, in different patterns and so forth. We want to reduce that whole thing to a sum over irreps with just one particle representation. Okay, so we didn't fully solve that problem, but we came very close to solving that problem in this paper. I won't go through the details, but the key ingredient was this coproduct. So the coproduct tells you how to take these more complicated states with different matter particles and simplify them, right, by killing one of the particles. And so by applying this coproduct, we were able to solve this sort of Clebsch-Gordon problem in some detail. And just to draw some pictures, if we consider some 4-point function, right? So here's some Euclidean 4-point function. It has two operator insertions. We can consider the state that appears now in the middle of this. By slicing open this diagram, we get some state in the middle, right? And the claim is that that state can be written as a sum over irreps, right? So that is this picture here. So we have a sum over some irreps that are labeled by n. And we calculated these gamma n. These are the Clebsch-Gordon coefficients that appear in our algebra problem. Okay. The other thing you can do is you can cut it this way, right? And that defines some slice with the gamma tilde n. Right? So there's two ways of cutting these diagrams. And it's guaranteed that these diagrams give you the same answer. This sort of crossing symmetry is guaranteed by this abstract property of the coproduct. Okay, so if you like, if you've seen 2D CFT, this will be very familiar. This construction allows one to define JT blocks. And the JT blocks are very analogous to the Virasoro blocks in two-dimensional CFT. The reason why I say they're Virasoro blocks and not conformal blocks is because the chord algebra contains the Hamiltonian, right? So a given chord block contains many insertions of the stress tensor, roughly, right? So it's more analogous to the Virasoro block in 2D CFT. Okay, but this was just an algebra, so if you didn't follow the details, don't worry. Just one more comment, which is we can characterize in some detail what are the actual operators that appear in this ODE. Okay, so what are the operators that appear in the intermediate channel? And this is where we found a little surprise. So the surprise is, well, first of all, the non-surprise is that we found some intermediate operators VWN, which are analogous to the standard double trace operators that you would expect in let's say, JT gravity with matter. But the surprise is that we found actually two kinds of operators for each value of n. Okay, so that's not what you would expect in ordinary field theory in AES2. And one combination just corresponds to, like, let's say the symmetric part of these two things, and another is the anti-symmetric part. Okay, and these extra operators that we found are going to be related to the inelastic states that explain that are related to the submaximal chaos. Okay, so that's just the little precursor. But now let's move on to the good part. So that was just some long algebra exercise. Let me summarize the situation. So first we motivated this whole discussion by considering the SL2 algebra of the wormhole and near extremal black holes. Okay? And we said that that was related to chaos. So then we took a long detour analyzing these chord diagrams and finding some sort of bigger algebra that we call the chord algebra. Now we're going to come back to the large P limit and try to find the analog of the SL2 algebra, which explains, hopefully, the submaximal chaos. Okay. So to do that, we searched for a subalgebra of the chord algebra that commutes with n bar, because that was the property that the SL2 algebra had. And we find exactly these generators. So these generators, J, obviously commute with n bar because they are made out of one creation operator and one annihilation operator. So they commute with n bar, they do not change the chord number, right? In the lambda goes to zero limit, one of the four J's that we can define becomes null, and there are only three interesting operators, E, B, and P. So they're defined like this. So JLs are just these expressions, they are just consist of creation and annihilation operators. And these three operators satisfy some algebra. Okay? The algebra that they satisfy should be valid at all temperatures because we didn't make any assumptions so far about taking low temperatures or anything like that. So we would like to know what algebra they satisfy. And to do that, we studied how these generators act on boundary operators. Okay. And what we found surprises. So what we found was that these three operators generate an SL2 algebra, where, let me skip ahead real quick. So they satisfy, well, maybe I won't skip ahead. So they satisfy some relations. They act on states with one matter particle in a very simple way. So let me explain this picture again. So we have some circle where we are considering the bottom of the circle to be the ket and the top of the circle to be the bra. And then we insert a generator, either E, B, or P, right? And we study how those generators act on these states. So we study the matrix elements of those states. And what we find is that acting on these one particle states, we have some very simple expressions. Okay, these simple expressions look like the SL2 generators on a circle, the standard SL2 generators on a circle. But the surprise is that the circumference of the circle, which we derived by studying the action, is not actually the physical circumference of the circle. Okay, so that is related to the fact that there's both theta in this expression and phi. So we found some SL2 generators that involve phi, which is linearly related to theta, but there's some shifts, and the total circumference of phi is different than the circumference of theta. Okay, the circumference of that bigger circle, so in particular, when we insert these generators, it acts as the standard SL2 generators on a bigger circle where we insert some fake region between the bra and the ket. So here are the physical regions of the bra and the ket in solid curves, and then we have these dashed lines, which are something that we artificially inserted by hand. And we did so because by inserting these artificial fake regions by hand, we got a very simple form for the SL2 generators. Okay? So that's just something that you can mathematically do. But of course the question is, what does that actually mean? Right?
You may be about to talk about this, but what about if you conjugate by e to the phi p or something to take one of the real points into the fake region?
Yeah, so we'll discuss this in 1 second. All right, but before I get there, let me just say that the circumference of the fake disk is exactly beta over v, where v was the chaos exponent that we were after. So now that explains the some maximal chaos. So in particular, what was the loophole in the previous argument that SL2 gives you maximal chaos? It was the assumption that the boost generates the usual, the boost is related to HR minus HL in the usual way, with the factor beta over 2 pi. But here, the boost acts in such a way that its period is a little bit funny. It's not, 2 pi, but 2 pi v over beta, right? Or it's beta over 2 pi v, sorry. So this extra factor v appeared in the calculations, right? And because the SL2 generators satisfy this unusual relation, we actually get the chaos exponent 2 pi v over beta instead of 2 pi over beta. So this is some sort of geometric explanation, but it is unfamiliar. Now, before I get to what happens when you act with the particle and so forth, let's just do some quick sanity checks to make sure that we understand what we're talking about. So a simple consequence of the SL2 symmetry is that the 2-point function should be conformally invariant on the fake circle. So that is actually a true statement. The 2-point function in large P SYK has this very simple form, which is a conformal 2-point function, except that it is conformally covariant on the fake circle and not on the usual circle. So usually we write this in terms of the Euclidean times, and there's some offset here. But when you define it in terms of the fake circle, there's no offset that appears. Now, that we already knew from a long time ago, already in Madison and Stanford. So we tried to see if there's some new consequence. And one of the new consequences that we found was that the 4-point function is only a function of the fake cross ratio. So that was something that we did not know before doing this analysis. So in particular, if you consider the commutator OTOC, this is some 4-point function divided by some products of 2-point functions, you find that it is exactly a function of only the cross ratio. No other temperature dependence appears, no other angular dependence appears except through the cross ratio defined on the fake circle. So it's important here that chi is the cross ratio on the circle and not the fake circle and not the physical circle. Okay? And furthermore, if you actually, so it's a very simple function of the cross ratio. And it turns out that if you expand this function in conformal blocks, the things that appear here, c squared k, are nothing but the Clebsch-Gordon coefficients to this algebra problem that we described earlier. So we can say that we not only explained the fact that it's only a function of the cross ratio by appealing to this algebra, but we can say that by analyzing this Clebsch-Gordon problem that I described earlier, we can predict all the OPE coefficients that appear in the 4-point function. And they agree. They agree in the lambda goes to 0 limit, which is when we get this fake disk. Now let me address Jeff's question. So suppose we start with a ket vector, right, which has a particle in the real region, and we act with the symmetry generator to translate it into the fake region. What happens? Right? So there's actually two descriptions of this. There's actually two descriptions of what happened. So first, we can consider the more conservative thing, which is just to stick with the chord Hilbert space. Okay, the chord Hilbert space is well defined for any finite value of lambda. Now, the fake disk holds at very tiny values of lambda, but that's okay. We can numerically take lambda to be very tiny and n to be very large. That should be a good approximation to the fake disk geometry. Okay? So the upshot is we can study a wave function let's say, which is localized in the real region. So that's, let me draw the oracle now. So we have some Einstein-Rosen bridge, right? It connects the two sides. This is the left, this is the right. We have some particle. We act with a symmetry generator that wants to move it into the fake region, right? So it starts to move it. What happens? First of all, nothing really happens. It's just a Gaussian wave packet that's moving to the right. Okay. But then what happens when it enters the fake region, and we continue to translate it beyond the physical region, is that the wave function goes crazy. Okay. By going crazy, I mean that this thing starts to oscillate rapidly. Number one, and number two, the numerical value of the wave function is enormous. So here it was very small, and now it's like some factor of 10 to the 18 bigger. Okay, so that's what happens when you take the simple state and you activate it with a symmetry generator going into the fake region. But it does so in such a way that overlaps of these states are governed by the geometry of the fake disk, right? It's the overlaps of these states are basically two-point functions, and those are governed by that simple formula that you got on the fake disk. So, in other words, the chord Hilbert space realizes somehow this fake geometry, but in a highly non-trivial way by arranging for this crazy-looking wave function, which is designed so that its overlaps with standard states, the states that are in the physical region, mock up the two-point function in some fake region. Okay, so here's another way to depict it. So, let's say in the first way of depicting it, we started with a particle that was well localized. We translated beyond the real region into the fake region, and we got some wave function that was something crazy. It looked highly oscillatory, and I didn't think that on the left. There's another way to think about it, though, which is we have a particle which is now localized just in the fake region. So we extend the Hilbert space, and we allow for particles to be localized in the fake region, and we do so in order to explain all of the endpoint functions that we derived in the previous slide. But you can say this is just a trick to explain some very complicated wave function on the left. But on the other hand, if you want to do that, be my guest, but it's very difficult to see why this crazy-looking wave function in the left picture has any geometry associated to it at all. So you can sort of pick your poison if you want.
In the limit lambda goes to 0, do the overlaps of the fake disk state with any fixed, like real disk state go to 0?
No, they don't. They don't. So they actually stay finite.
They stay, okay.
They can stay finite. So in particular...
So no, what I mean is... Sorry. What I mean is is it possible, does that crazy wave function have a nice limit?
Yeah, the wave function does not, but its overlaps does.
Yeah, but the overlaps could be computed in the fake disk picture.
That's right.
Right, so it's like the fake disk picture becomes, it's like a non-isometric code or something. That's
something like that.
Exact, but
Yeah, something like that.
They're not really independent states, but you can treat them as that. And
that's right. Yeah, they're somehow, yes.
Will you observe some difference in the correlation functions for this fake wave functions versus the fake wave functions? If you scale the number of operators in your correlators with Q or some parameters?
Yeah, that's a good question. I don't know the answer to it. Yeah, we only consider the limit where you consider finite number of particle insertions. But yeah, it would be interesting, I think, to either scale up the number of particles or just take one particle with many,
right.
like a very heavy operator.
Because it's clearly that there are different Hilbert spaces,
yeah.
Right? The fake Hilbert space versus the real Hilbert space. So somehow you should see the different details.
Well, I think the fake Hilbert space is like a continuum description of some discretized thing, right? So it's at some limit, yeah.
Right.
But if you kept it discretized and then looked at a fake Hilbert space with it discretized, then I would guess if you looked at sufficiently complex enough operators, then you'd see the fake Hilbert space break down. At that point, the fake Hilbert space would explicitly be bigger. So
Probably, yeah. I mean, yeah. Well, okay, so I will now explain one more thing and then we'll end. So there's a related aspect of the fake geometry which is negative lights. Okay, so let me explain this in a very simple physical context. So the context is we start with the thermal field level. Let's say we go back. Here's the thermal field level in Lorentzian time. So this is Lorentzian time. We go back in time and we insert a particle on the left and a particle on the right. Okay. at early times. And they scatter, right? They scatter in the wormhole. So now we can ask, what is the geometry on the different slices as a function of Lorentz time? Right? That's a totally standard question. We don't have to analyze this in JT, right? But in this limit, we get something pretty weird. So let me try to explain why it's weird. The rules for the Hamiltonian, the left Hamiltonian H left, are such that if you have a matter particle, let's say a red particle, well, it doesn't matter. If you have a particle in some particular ordering, it can never change the ordering of those particles. So that's because it just had these creation and annihilation terms. There are no terms which allow the ordering of particles to change in the Hilbert space when you act with the Hamiltonian. So that means that no matter how far we go up in Lorentzian time, this particle, which looks like it should be to the right of this particle, actually has to stay to the left of this particle somehow. And the only way for that to happen is that the way it works out is that there's actually some sort of negative length between this particle and this particle. So this is just some sort of aside, but it actually, yeah, the more accurate picture is that, so the naive picture is that these two particles just pass through each other, right, at atoms. That would be like the JT picture. But the more accurate picture is actually that the blue particle is always to the left of the red particle, but that's because there's some sort of negative link that connects the two particles. Okay? And we think that this kind of negative length actually happens in simpler contexts. For example, in the previous slide, we can actually compute the length between this particle and the right boundary. And we can confirm that it's actually negative. So if you translate particles into the fake regions, you can get negative lengths. If you want, you can ask me more about that. So in conclusion, the fake disk makes some maximal chaos manifest. It seems to be a geometric representation of some subtle states in the continuum limit. So these are some states which naively look like they're very high energy states because they have a rapidly oscillating wave function and so forth. But secretly, they're actually low energy states. And the fake geometry represents, it's sort of an efficient way to represent those states. It's a bit similar to the chiral fermion problem, if you're familiar with that. So in the chiral fermion problem, you start with some lattice, right? And you think, oh, I only have left movers. Okay, I only have left moving fermions. But the problem is that you can have wave functions which oscillate on the lattice scale that represent right moving fermions, right? So the naive low energy limit, you might, in the chiral the statement is that in the naive low energy limit, you might think that your lattice only has left moving fermions. But if you actually analyze the low energy limit correctly, you will find that certain states which oscillate rapidly on the lattice scale should actually be included in the low energy description, and those are the right moving fermions. So here the analogy is that the subtle states, the ones in the fake regions, are like the right moving fermions. They oscillate on the sort of lattice scale, and we didn't think that they should be there, but by analyzing the symmetries and so forth, we find that they have to be there. So a general question is whether this has any lessons for submaximal chaos, let's say in string theory or other contexts. I would like to not answer that question, but instead just say that we go back to the slide in the beginning. We had these three features. We had propagating matter involved, we had bulk discreteness, we had submaximal chaos. And we sort of understood some aspects of these features by analyzing this Q-deformed symmetry algebra, which I think we are just scratching the surface of. So anyways, thanks very much for your attention. Yeah.
Right, questions?
So as you do that trick of like translating into the fake region, did you study at all how the amplitudes or the frequencies of the wave functions grow? Or do those match what you'd expect based off the based off time equation?
Yeah. So the frequency, what actually happens is this wave function actually just has a -1 to the n factor. So if you multiply this by -1 to the n, it's a smooth wave function. But the amplitude is still huge. Okay, so the amplitude here is 10 to the 18. It seems to get worse and worse as lambda is smaller and smaller. But what we did was we computed numerically the overlaps of these different states, and we saw pretty good evidence that they reproduce the overlaps. So they seem to be converging to some answer, and the answer that they're converging to is the fake disk answer. And well, we checked this at many decimal places in some cases. So we were convinced by that. And then, well, Douglas also, in some special case, was actually able to solve the Q recursion relations for how the symmetry generators at finite lambda act on one particle space. So again, in some special case, we were able to do the analytic computation and show explicitly that the overlaps converge to the fake disk answer. So we kind of worked it out in the general case, but it seems very likely that it will converge to the. Yeah, I guess we could look at the formula and address your question more quantitatively, like how the wave function behaves and so forth. I don't remember all the top of my head.
Yeah, this is very right. Mechanism interior, but on the boundary.
Yeah.
And yeah, of course, horizon state, coherently.
Right.
And also related with, it might be on disease. It's always like, from policy point of view, red, blue, really just go through without breaking. And it looks like from target space point of view, it looks like rings.
I think, yeah, there's these papers like Kubowski and company.
Yeah, it's a very.
Yeah, where they have these zigzag strings.
Yeah, structures pretty.
Yeah, we were one that was also.
Yeah, and also interior black hole seems like without including gravity, because it's all on the boundary. This phenomenon you see without.
Yeah, what's weird is that the spatial region is like, yeah, I mean, it's related to the black hole, but it's also.
It's not directly,
yeah,
right?
it's kind of,
because boundaries are no gravitational theory. It's simply some new spatial region.
New spatial region that can converge in this finite temperature limit.
Yeah, that's the only common thing. It's not well at all.
But I agree that it definitely seems reminiscent. Yeah. In particular, there's some states which, if you're not very careful, they seem to become null states. So that also, well, of course, yeah.
Yeah, I'm not asking anything.
So Henry, if you just compute the norm, the inner product of one of these fake disk states with itself, you'll get something really big, if I'm understanding correctly. The wave function really big is just a -1 to the n that will cancel out in the.
Yeah, so you're asking why it's not huge, despite.
Yeah.
Yeah, so the reason is actually because the inner product is non-trivial. So I didn't explain this. But
good.
Yeah, and that smears out this
Yeah,
thing.
yeah.
And by smearing out this thing, it effectively kills the amplitude.
Yeah.
And gives you something that's
Yeah.
right.
So it's okay, cool.
Yeah, I did not bother. I skipped a lot of the.
Yeah. The other thing I was going to ask is, this is not really related to your talk, but how do you think about the submaximal chaos in string theory? Do you have any? Yeah, you want to connect to it. I feel like I've worked through the calculations in Douglas and Steve's paper and never got anything out of it.
Yeah. I kind of shared that feeling.
I don't even have a good intuition for why it's the ratio of the string scale to the ADS scale.
I also agree.
Okay, that's fine. If anyone else has any intuition, please let me know, because I'd love to understand it.
But correction has to go to 0 in any case.
But like,
I can tell you why it's L squared, right? Because it's alpha prime. That's not all string theory.
What you're doing here is very different. You're changing the acid product. The length is changing due to the printing company. It's very different from changing the straight line.
Well, it's a bit similar in the sense that for near external black holes, there's something special that happens, which is the string scale to the ADS scale is, let's say 1. In the near extremal limit, you still have maximum gains. So that is something special. And if you like, the fact that when you make the temperature finite, you're just revealing the fact that, the formula that I wrote down was for, like, let's say ADS5 times S5. Okay, for a Schwarzschild black hole at ADS5 times S5, we expect something like that. But for a near extremal black hole, we expect something different. We expect that no matter, as long as the string scale over ADS scale is fixed, let's say, when you go to very low temperatures, the theory becomes maximally chaotic. And that's because the Schwarzschild mode is enhanced, so it dominates the signal. So in the OTOC, the most important thing is the Schwarzschild, and the fact that there's like all the stringy stuff is disguised, it's sort of buried in it. So when you take the temperature to be higher, you sort of are reducing the dominance of the Schwarzschild mode and revealing more of the stringy physics. That's what people say, or that's what, let's say, Douglas and Steve say in their paper, or extrapolating their paper to the near external black hole case. Here, we're, so you could ask what is the string scale and so forth in the SYK model. But we don't really have a stringy model, but to the extent that we do, it would be something like this. So 1 over beta j would be the analog of the Tufts parameter in the SYK model.
Sorry, I didn't quite understand your comment at the end about the negative distance between the right physical point
Yeah,
from the
yeah.
thermal field level and the fake point.
Right. So the actual boundary is right here.
Yes.
So suppose, well, okay.
But then does it mean, so like you measure a correlation function and you see that the distance?
Yeah, let me be a little bit more concrete. So this was a little bit surprising. So what we literally did was we computed the expectation value of n right in a one particle state. So n right was the number of cores to the right of the green particle. Right? So n right has eigenvalues 0, 1, 2, 3, 4, 5. So it sounds like a positive operator. But it turns out that because it's a non-Hermitian operator, it can have negative expectation value despite having positive eigenvalues. So that is a fun fact about the near algebra that I also had to review. But yeah, so if you have some non-trivial linear product where NR is not a Hermitian operator, even if it's, yeah, this thing here can actually be negative even if all the eigenvalues of NR are positive. So the amazing thing is that is possible and that actually occurs, and the negative link that you get agrees, as far as we can tell, with the fake geometry.
But that means that the geometry is not really fake. The fake geometry is not really a regular geometry because
Well,
it has negative distances and
Something
part of
like
the
that,
geometry.
yes, something like that, yes.
Like maybe it means that part of the geometry is complexified.
Well, the picture is like we have some Euclidean black hole, right? And we are measuring this length, right, which is NR, right?
Yes,
and we
yes.
expect it to be positive, but if we act with a symmetry generator to translate this into the fake region, NR can actually become negative. So that's explained in this geometry by this particle being sort of beyond the boundary of the Euclidean black hole. So yeah, it is some, well, it's something weird. Yeah, and also, so that, you might say that that's some weird thing about the fake states, but my example with the Lorentzian scattering problem was just a simple way where you can generate negative lengths in some states which you would think are completely physical. Like you start with some Lorentzian contour where you insert state like everybody, like for example we do and other, many other people do, right? Where you insert states in the Lorentzian past and you let them collide and you just naturally generate somehow a state with negative length. So it seems to be somewhat common in this weird bulk dual with SYK. So yeah, I agree, it's very strange. And there's actually even, yeah, well, let me leave it at that. Yeah.
Any other questions?
Are there any, are there any constraints on how negative the length can be? Like, can it not get more than a scrambling time, whatever that would mean there, or anything like that?
It seems like there should still be some constraints by considering like n and dagger, right? So that's an Hermitian thing.
Okay.
I think I thought about this at some point, but I don't have anything sharp to say.
Okay, let's thank Henry again.